start with this KKT conditions and a general optimization problem. So a general optimization problem can be written like this, like, let me take this. Okay, so we can write it like minimization of f(x), any function subject to some equality constants, hx equal to 0, along with some inequality constant gx less than equal to 0, right? And this function f is a function from Rn to R, h is a function from Rn to Rm, and g is a function from Rn to Rp. Okay, so basically there are m equality constants and p inequality constant. This can also be written like this: minimization of fx subject to hix is equal to 0, where I is equal to 1 to m, right? And gix is less than equal to 0 for I equal to 1 to p, right? So we have p inequality constants and m equality constants. So this is a general optimization problem. And this general optimization problem, if we talk about this optimality condition or a convex optimality condition, so basically what we see that this inequality constants are convex. Suppose we have convex functions here and this equality constants are affine, that is we have linear functions, then we have the result. So what is the result? Let me just very important. So okay, so we understand that all these functions are differentiable. So let me write it directly. That is, suppose there exists this x bar in K and lambda bar in Rm and this mu bar in Rp, right? Such that the first thing that happens is this mu bar is greater than equal to 0. The second thing is gradient of f at x bar plus lambda bar transpose gradient of h at x bar plus mu bar transpose gradient of g at x bar is equal to 0 or 0 transpose. This can also be, okay, let me first write it down, then we can write the equivalent formation that mu bar transpose g x bar is equal to 0. Okay, so what will happen then? X bar is a global minimizer of f over k, global minimizer of f over k. So the component wise we can also write it like mu bar I is greater than equal to 0, where I is equal to 1. So mu bar is for g, so I is from 1 to p, right? I is from 1 to p, and here also we can write that mu bar I and gi x bar is equal to 0 for I equal to 1 to p, component wise. We can also write it in form of component, and here if you write it component wise, it is something like gradient of f of x plus this will be summation lambda I bar gradient of h x bar, where this I is equal to 1 to m. For h it is 1 to m, and here you can write summation mu I bar gradient of gi x bar, but this I is from 1 to p, right? And this is equal to 0. So we can also write in transposition form like matrix multiplication, or we can write it in summation form. Both the things are equivalent. But of course, this is a convex optimization problem. The functions are convex, and this visible region K is also convex, right? So what will happen that, let me give you the proof and then we can discuss the result, like what we are going to do. So by convexity of F, one has, so convexity we know that F of X is greater than or equal to F of X bar plus this gradient of F at X bar X minus X bar, right? This is true for every X in K. This is one, equation number one, because F is convex and this inequality we are using. So by condition 2, see, by condition 2 here, this one. So in place of gradient of F at X bar, we can write this term. This gradient of F at X bar is equal to minus of lambda transpose H and mu transpose G, right? So by condition 2, one has, so we can write that this F of X minus F of X bar is actually greater than or equal to, here we in this place we can write minus lambda bar transpose gradient of H at X bar and minus mu bar transpose gradient of G at X bar, and then we can write X minus X bar. We can also write it in form of transpose, right? So this is equation number 2, okay? And also we have this expression number 3, that is because the function H is linear. This function H is linear, right? So what we can write that also this gradient of this, or we can write lambda bar transpose gradient of H at X bar X minus X bar is equal to 0, right? This is because it is a linear function and the value at every point is 0, so we can always write it like this, right? So first we claim that, and we have to claim that this mu bar transpose gradient of G at X bar X minus X bar is actually less than or equal to 0, right? This is expression 4. Because here, if this is 0, then this value is less than or equal to 0, so this value will be greater than or equal to 0 and it will be a global optimal solution, right? But so these two things must be satisfied. So if we go for this one, expression number 4, so you can observe that K is a convex set. Since K is convex, therefore one has, we can write X bar plus lambda X minus X bar belongs to K for every lambda in this open interval 0, 1 and for every X in K. Is it true? Because K is a convex set. So by, hello, yes, any query? So therefore, see, this point belongs to K, and therefore the value of G at X bar plus lambda X minus X bar will be less than equal to 0, because we know that this is the feasible point for every lambda in 0, 1 and for every X in K, because this point belongs to K. So, and this is the problem, the value at any feasible point is less than equal to 0, right? So this is less than equal to 0 for every lambda in 0, 1. So by condition 1 it follows that, see this condition, if it is greater than equal to 0 and this value is less than equal to 0, so you can multiply, you can always multiply with this lambda, right? And what will be the value of g of x bar? So the value of g of x bar is this convexity, right? The value of g at x bar will be this convex function. So this will be like so from here, if we write it like this, as we have done in the previous problem, so g of x bar is less than or equal to 0, which is equal to g of x bar, right? G of x bar. If it is equal to 0 for every, so let me write it down I here, I. If it is I, so this is for every I in 1 to m, right? Here we are taking, okay, we are taking p. So every I in p. So capital P, we denote the set of all indices p. So here it will be 0 for every lambda in between 0, 1 and for every x in k, along with for every I in this we call px bar. So what is px bar? This is defined as all the I in p such that gi x bar is equal to 0, where this value, that is active constants. Basically this is the collection of all active constants, right? So if it is the collection of all active constants, then again we can write gi x bar plus lambda x minus x bar. Then you can take this minus gi x bar, and then you can divide with this lambda. This is less than equal to 0 for every x in k, and for every lambda in open interval 0, 1, and for every I in p of x bar, right? And if you take the limit, as you have done in the previous case, taking the limit as lambda, so I think I should take another, because we have taken lambda bar here. So if you don't confuse with this notation, this is different. This is lambda, that one is lambda bar, right? But we can take some another notation like t or something. Let it be t, because then there should not be any confusion. This is t, because lambda we have already taken. Let it be t here, right? So this all will be t. So this is t, and here, yeah. So for every t, as so we take t, limit t as t tends to 0 plus, right? So if you take t, 1 has, so what will happen? This is nothing else but the gradient of gi x bar in a direction of x minus x bar, right? This is, you know, is less than equal to 0. So for every x in k, and for every I in p of x bar. And you observe that this, by condition 1, this mu bar is greater than equal to 0, every number. And here every number is less than equal to 0. So if you multiply with mu bar, so by condition 1 has, so if you multiply with this mu bar, you will get mu I bar gradient of gi x bar x minus x bar is less than, because this is negative, and if you multiply with a negative number or a positive 0 or positive number, it will still remain negative. So this is true for every x in k and for every I in p of x bar, where gix is 0. If gix is not 0, then this mu I bar will be 0 by this condition 3, right? So by condition 3, one has, so we can write this gradient. Okay, so we can just write for every value gradient of gx bar x minus 0 for every x in k. I think there is some issues with the this mic. Hello, Sonali, any doubt?
No, sir.
Okay. So we can always write it like this, right? So now this value is less than equal to 0. See, so we wanted to show these two things. Equation 4. We have proved equation 4. Similarly, you can prove this equation 3. So if you use this 3 and 4 in this expression 2, one has, so using 3 and 4 into one has, so one can write that f of x is greater than equal to f of x bar for every x in k, and that implies that x bar is an optimal solution, right? Is it clear? X bar is an optimal solution. So this result is known as sufficient condition for KKT theorem, right? KKT optimal solution, and actually we can use this result to find out whether a given problem is convex or not, right? And then we can use this result to observe whether for example, if you just want to consider that what is happening, so you just take a problem minimization of f of x1 x2 is equal to x1 square plus x2 square plus x1 x2 minus 3x1 subject to x1 comma x2 greater than equal to 0, right? So here we actually can observe that this f of x1 x2 is this function x1 square plus x2 square plus x1 x2 minus 3x1, and then one can take one function g1x. g1x is equal to minus x1 less than equal to 0, and g2x is minus x2 less than equal to 0, right? So this is a problem like this. Here we don't have this equality constant but two inequality constant, right? And then we can find the gradients of this number, gradient of f at x. So it will be 2x1 plus x2 minus 3, and then with x2 2x2 plus x1, right? And then we can have the gradient g at g1. So this g1 will be like minus 1 0, and this gradient of g2 x, it will be 0 minus 1, right? So we have all these numbers, and then we have to find out the variables, this Lagrange multipliers. So we have mu1 gradient of g1 x and mu2 gradient of g2 x equal to 0, because we have only one. So with g1 the multiplier is mu1, with g2 the multiplier is mu2, and we have to solve this expression. So if you substitute all these numbers, like you will have 2 x1 plus x2 minus 3, then you have minus mu1 equal to 0, and the other one will give you 2x2 plus x1 minus mu2 will be equal to 0. And along with this, you have one more condition that mu1 is greater than equal to, and mu2 is also greater than equal to 0, right? So what will happen, suppose, so we have these conditions that, and you see these are two equations. And how many variables are there? 1, 2, 3, 4 variables. Okay. So this is important, two equations and 4 variables. So the degree of freedom is 2, right? So we can take any two numbers and make them 0. So suppose mu1, see this mu1 is 0 and x2 is 0, right? So if you substitute like mu1 equal to 0 and x2 equal to 0, you will get that this x1 will be 3. Okay, so this x1 will be 3 by 2 and this mu2 will be 3 by 2, right? Is it clear? And then if you take mu2 equal to 0 and x1 equal to 0, then you will get that x2 is equal to 0 and mu1 is minus 3. But you see, this is possible. This first condition is possible because this mu1 is greater than equal to 0, mu2 is also greater than equal to 0, and these are feasible points. But this is greater than equal to 0, right? So actually when you take this greater than equal to 0, so what is the feasible reason? This is the feasible reason. And the corner point is this one, 0, 0. So we want to check the possibility of 0, 0. But here, this is not possible. Not possible. Why? Because you see this mu1 is minus 3, but negative values are not permissible. Scalar multiples cannot be negative. So this is one possibility. So what is the possibility? X2 must be 0 and x1 must be 3 by 2. 1, so this is 2 in between, this is 3 by 2, right? So 0, 3 by 2, or sorry, 3 by 2, 0. This is 3 by 2, 0. So what does it tell? That we can have this optimal points in the not only at the corner points, but this can be interior points as well, right? So this 3 by 2, that tells that 3 by 2 comma 0 can be a minimizer. And if you observe that whether these functions are convex or not, so you will see that this is convex and these are also convex functions. This f, g1, g2, these are convex functions. So due to convexity, you will observe that these are convex functions, and due to convexity, this will be an optimal solution of the given optimization problem, right? So this is how we use this KKT conditions to solve the optimization problems under convexity assumptions. Okay. So for the time being, I am done with this. The thing I wanted to tell you about this convex sets, convex functions, and then convex. If you have any queries regarding this, you may ask. Thank you for your listening.
Application of convex function.
Applications of convex optimization, you mean?
Yes, sir.
See, there are plenty of applications of convex programming actually everywhere. So have you learned this linear programming problems?
Yes, sir.
So you know the applications of linear programming problems are in different fields, like you can go for this this production problems.
Yes, sir.
Production, you can go for production or you can go for manufacturing,
Yes, sir.
right?
Yes, sir.
Or you can go for agriculture,
Yes, sir.
agriculture, and you can go for finance,
That's
finance,
good.
and you can go for, and so on,
Yes,
so
sir.
on and on, right? There
Yes,
are
sir.
plenty of applications, but in real life situations, suppose you have a function like f of x and it is c1 x1 plus c2 x2, something like this, right? So
Okay,
what
sir.
is c1 and c2? This is the cost parameter, right?
Cost
But in
variable. Yes,
general,
sir.
as you know, for example, suppose you want to buy petrol, okay,
Yes, sir.
or you want to buy pulses, then what happens that the prices are not fixed, the prices are not fixed. Here we are taking these variables as a fixed variables, okay, for the
Okay,
sake
sir.
of simplicity to understand what is happening. But in real life these parameters are not fixed. So you know that today the price of petrol may be 99, tomorrow it will be 100, and day after tomorrow it will be 97, like that, right?
Yes,
And
sir.
similarly, you know the prices of vegetables and all those things, or medicines, even medicines in medical industry, you can have application. So it is possible that C1 is actually equal to some function of x1, and C2 is actually equivalent to some function of x2, right?
Yes, sir. Yes, sir.
That is, they are not fixed but a variable.
Yes,
And
sir.
suppose this is x1 and suppose this is x2, linear function. We are just assuming, but in real life it may be very complex function. So then what will happen, this C1 is x1 and this is again x1, and C2 is x2 and this is again x2. So what you have, x1 is square plus x2 is square, right?
Yes,
Now
sir.
the function is x1 is square and x2 is square. This is not a linear function, but
It's
this is a
non.
convex function. This is non-linear, and you can observe that this is a convex function, right?
Yes, sir.
This
Yes,
is a
sir.
convex function. And since this is a convex function, now you can apply the convex optimization. So basically all the things that you have learned in linear programming problems, in real life when you try to handle those situations are not linear but non-linear. And that is why you have to apply this convex optimization problem in different fields like production, manufacturing, agriculture, finance, medicine, everywhere. There is no field that where you cannot apply this. In
Understood.
construction, in topology optimization, everywhere you can apply this, right?
Yes, sir. Thank you, sir.
Okay, Akanksha.
Any doubts, class?
Sir, one more doubt.
Yeah.
Sir, can you clarify what is the difference between global maximization and local maximization? I think.
Yes, global and local, as I have discussed already. Like
Yes, sir.
suppose
But quite doubt.
suppose you have a damping function, like some damping function you take, like if you take sine mod of x or mod of sine x, right?
Yes, sir.
Something like, you take any damping function, something like this, and it goes on increasing like this, okay?
Yes, sir.
And as it moves towards the origin, it decreases. So every time you see here, it is a local optimal solution, right?
Okay, sir.
The meaning is that you have a neighborhood. On the left hand side, the function is increasing, and on the right hand side, the function is also increasing. Is it clear?
Yes,
The
yes,
left hand
sir.
side, the function is increasing, on the right hand side, the function is also increasing. So this point must be the minimizer, right? But in a
Yes, sir.
local sense. Why in a local sense? Because
Yes,
after
sir.
a certain time it decreases again, right? So you see
Okay, sir.
here, this function is increasing on the left hand side and on the right hand side. This here also it increases on the left hand side and right hand side. Here also the same thing. So these are local minimizers. Okay.
Okay, sir.
But the thing is that as you continue, this value is less than this value is less than this value is less than this value, and this value. So it will keep on increasing, right?
Yes,
These
sir.
local solutions will keep on increasing. And similarly, if you go toward the origin, these local solutions will keep on decreasing.
Yes, sir.
So you cannot have a solution which is global minimizer or a global maximizer. Are you getting the point? But in a neighborhood, it can be local. It is increasing on both the sides. So that is why it is. And
Local
similarly for the
minimizer.
other, yeah, similarly for these points.
Local
These are
maximizer.
yes, very good. So these points are local maximizers. So this is how the things are increasing. So that is why they are local in the sense, but we cannot find a point because it will keep on increasing in this line. And
Yes, sir.
similarly, this will keep on decreasing on
This
this line.
region.
Yeah,
Yes, sir.
this region, like this.
Thank you, sir.
So we cannot have a global optimal solution. So this is the difference between local and global optimal solution.
Thank you, sir.
Okay, thank you. So Guru Prasad is also here. Nice to see him as a faculty. Yeah. Your mic is off, Satyendra. Your mic is off. Yeah.
Okay, thank you, sir. जिस तरीके से क्वेश्चन बच्चों ने पूछा तो मुझे लगा कि बच्चों ने बहुत कुछ सीखा है आपसे.
Yeah, that's good.
से हम लोग भी सीखते रहते हैं.
No, I also try to learn with each and every presentation because then the audience is different and we also learn a lot.
Yes. तो मैं अपने सभी पार्टिसिपेंट्स और अपने आज के मुख्य वक्ता प्राचार्य सर के एक औपचारिक धन्यवाद के लिए अपने सहयोगी डॉक्टर गुरुप्रसाद सिंह सर को आमंत्रित करता हूं. सर प्लीज.
Good evening, good afternoon to all. First of all, I am very much grateful to our professor, Dr. P.N. Dogre sir, who has permitted us to conduct this online weekly lecture series. And I'm also thankful to Dr. Sridhar Yadav sir for chairing the lecture. And I also extend my heartful in the keynote speaker today, organized by our Department of Mathematics. Because in the continuation of the lecture on the topic convex programming and non-convex programming, we have a very simple lucid manner which is shared to all the audience here. So thank you so much, sir. For such
So थैंक यू गुरुप्रसाद सर, इतने अच्छे से सबका थैंकफुल बोलने के लिए. मैं अपने तरफ से भी सर का एक बार और धन्यवाद देता हूं. और हमारे साथ ज्ञानपुर भदोही से डॉक्टर जितेंद्र मौर्य सर जुड़े हुए थे. मैं उनका भी धन्यवाद करता हूँ। हमारे प्यारे बच्चे जो कि इस कार्यक्रम के बैकबोन हैं, मैं उनका भी बहुत ही स्वागत करता हूँ, साथ में धन्यवाद करता हूँ, जो इतने मनोभाव से इस लेक्चर को सुनते हैं, समझते हैं और सवाल भी करते हैं। बहुत बहुत धन्यवाद सर।
Thank you, Satyen, for taking all this pain to organize this type of workshops online, because it's not always easy task to organize workshops and lecture series. So we all must thank you as well for taking all this pain to organize this. And thank you, Guru Prasad, for your kind words. And see you all sometimes somewhere, right?
Okay sir,
So have
thank you.
a nice day.
Okay participants, thank you once again.